by a very brief summary of what we have done last week, and this is going actually an incomplete summary, and this is going to be some kind of introduction to what I'm going to tell you about today. Okay, so what we focused on last week was autoencoders. So what are autoencoders? So here is the, let's say, the simplest architecture of autoencoder you can think of, where you have an input layer, an output layer, which is exactly the same size. And in the simplest setting, essentially what you want to map is the input onto the outputs. And you would like the output to be as close as possible to the input. And obviously that would be a trivial thing to do unless you impose some kind of bottleneck in between. That is, the machine has to compress the information contained in the input in such a faithful way that the input can be reproduced on the output layer as close as possible to the true input. So how this is done? So I mean, we studied in detail what happens when the machine is linear, and we saw that this is basically principal component analysis. And then I told you about the non-linear cases and the connection with Hebbian learning and feature detection. So here is essentially how it's done. The hidden layer, or let's say the representation layer, computes the activity of the different units as nonlinear function of the input activities. So typically, some hidden unit here will be a nonlinear function of a weighted sum of the input units here. This is called H. And then another nonlinear function, a priori nonlinear, is introduced to compute the activity of the output units. And essentially, the different weights here, that is the connection between the layers, n and m prime, should be learned by minimizing some kind of loss function. And the cost here is the difference between the input and the reconstructed inputs. That is what is on the output layer. Okay, so that's something we discussed about last week. And as I said, this original formulation is not optimal in the sense that obviously if the size of a layer here is very short, and this is what you would like to have, because otherwise you are not coding anything, you are just reproducing, then of course perfect reproduction will be very hard. So actually this kind of architecture was, let's say, improved with the concept of sparse autoencoders, where now there is no restriction on the dimension of the internal layer here, of the representation layer, but there is a restriction on the activity inside this representation layer. So the idea is that you have many different possible representation. So this possible representation actually tells you how some features which correspond to the connection of each hidden units to the onto the input layer are present in the data, in some particular data item V, which is presented on the input layer. But what you expect is that not all features are present at the same time in the same input configuration, so that the activity here will be quite sparse. So even if the dimension of this hidden layer is very large, only a few hidden units will be activated, and you would like to reconstruct the input from that. So there is a large diversity of possible features, a large dictionary, but not only a few words are used at the same time to reproduce a configuration. So this is the basic idea of sparse autoencoders. So this is essentially the same idea as before, but instead of minimizing this, now we are minimizing something which is very similar, plus some penalty, which is imposing something about the sparsity, or let's say some constraints on the activities of the hidden units. And in fact, the next step, when you see that, is to go to what is called sparse dictionary learning. So this is essentially the same idea, except that actually, if we think about that, we can forget about this condition here and say, okay, I have some inputs here. I'd like to find some representation in this hidden layer, such that from my representation, I can reproduce the inputs, but this representation has to satisfy some constraints, like sparsity or whatever I want to impose. So the idea is to have some machine like that, where you have an input layer, a hidden representation layer, and you would like to minimize some kind of cost function over the weights which connect the inputs to the hidden units, and with some sparsity constraints here. So essentially what we find is a machine with a bipartite architecture here in the simplest formulation. And this is what I would like to tell you about today. So I will do that in a specific setting, which is restricted Boltzmann machines, which were introduced a long time ago. Actually, this machine was introduced about 30 years ago, but for a long time they were not used, and then they came back to life, let's say, about 10 years ago, and they are somewhat less used now, but I will tell you about that in the next slide. Okay. Okay, so what I will focus on today is this kind of architecture, which is called restrictive Boltzmann machine. So it's an example of Boltzmann machine. So what is a Boltzmann machine? This is essentially for Earth-ionizing model, statistical mechanics. But there are hybrid machines in the sense that not all units should be binary units. They can take different values. So let me be more precise. So the machine is made of two different layers. One is the input layer, which is called also visible layer. So visible means that all the data we have in order to train the machine are on this layer here. They will be displayed on this layer. And we have another layer, which will be the representation layer, which is called hidden layer. So hidden in the sense that we don't have any data on the values of these units here. And we have connections in between. So the machine is essentially a statistical mechanics model. So and it's described in terms of a joint probability between the configuration of the visible units here and the hidden units here. So P of V of H, P of V on H, is going to be the Gibbs distribution, or let's say you have the Boltzmann weight here with an energy which is correspond to this bipartite model. So you have three kinds of terms. First, you have a connection term, which tells you how visible unit I is connected to hidden unit mu with some weights here. Then we have local potentials acting on the hidden units and on the visible units. So here, in the first part, before the break, I will consider the case where the visible units are binary units, 0, 1, or plus 1, minus 1. But of course, this is just to make notation easier. And you will see in the applications to protein data I will show after the break, in fact, the visible units will take 21 different values because they correspond to the 20 amino acids plus a gas symbol. I'll come back to that. Okay, so here, let's say just binary variable. So if you have a binary variable, the most general potential you can think of is just a local field, okay, because there are only two possible values, so you have to specify two values of the energy. So I will call Gi the local field, and then on visible unit I, and then I have a potential U of H, which is acting on hidden unit number mu here, so it's a U mu of H mu. So I will specify the potential which are chosen here, because actually the choice of potential is very important. So the important point also is that H mu is not restricted to be a binary. It can be, it depends on the potential, but it can be a real variable. So this machine was introduced a long time ago. The first paper, which is some kind of strange paper by Smolensky, which is some kind of half philosophical paper in 1986, but it comes 1 year after the paper by Ackley, Hinton, and Sejnowski on Boltzmann machine. And this is just a specific case of Boltzmann machine where you have no connection within the layers here. Okay.
What's the meaning of restricted?
Yeah, restricted means no connection within the layers, only in between the layers. Okay. So let me just tell you a few things about these machines. And so first of all, so what are the advantages of this architecture? So I will insist on the fact that they are very similar to the autoencoders. In fact, they were built for exactly the same purpose. But let's look at some technical details first about sampling and learning. So what about sampling? So the fact that the architecture is bipartite makes the sampling easy, or let's say easy to formulate and to do. That doesn't mean it's fast, okay? So let me tell you more precisely how it works. So here I have represented in this graph here the whole visible layer as a single blob, okay? This is not a single unit here, that's the whole visible layer. And this is the whole hidden layer and the whole visible layer again at the next time. So here's the idea. So start from a configuration of a visible unit, so a bunch of zeros and ones. And if you fix this initial configuration here, then you see that all the hidden units are independent from each other, conditioned to the visible configuration, simply because they don't interact together, right? So that means sampling the values of the hidden units here is very easy. So this is written here. So let me fix the value of the VIs, initial condition. I will compute what I call here the input to hidden unit mu, and the input is just a sum, it's just a weighted sum of the activities of the visible units weighted by the connection to hidden units mu, Wi mu Vi. So it's a real number. Then I will compute the activity of hidden unit mu conditioned to the V's, that is to the input here, by sampling from this scalar distribution. So it's a density, probability density here, which corresponds only to the h mu part of this energy here. So you have minus the potential, u mu of h mu, plus what depends linearly on h mu from this part here, and this is only h mu times the input on two active hidden unit mu, right? And all the other hidden units, they are just disconnected from that, so I don't care about. So sampling from that is actually easy. It's just, you know, a 1D distribution, so you can sample from that quite easily. Then once you do that, you get the value of h mu, one possible realization, and you do that for all mu's. So you get one realization of the hidden unit configuration, right? And then, of course, this is bipartite. So this is purely symmetric, completely symmetric. So you can repeat the same process and sample from the visible configuration, visible layer, exactly in the same way. So now what I do is that I will compute the input coming onto visible unit I, which is just the sum of a mu w I mu h mu, and I will sample the activity of visible unit I from this distribution here. Okay, so there is a local field, which is gi, which was the local field which was written here, plus an effective local field, which is the contribution of the hidden units. Okay, so you choose 0, 1 with the corresponding probabilities, and you get a new configuration on the visible layer, and so on. Okay, so essentially this is what is represented here. Start from a visible configuration, sample the hidden configuration, sample back the visible configuration, and go on. Okay, and here that's just a number of sampling steps. So now, what is the meaning of all that? So what we can expect from all the discussion we had about autoencoders and so on is that when I start from my data, which are presented on the visible layer, then if my machine is trained properly, if it does a good job, it will compute some representation of the data. And I'm expecting that this representation has some meaning. So if it has some meaning, that means that I will extract some statistical important features from the data and the different h mu's, which tell me what are the degrees of the presence of all these features mu's in the data configuration. Then the next step is interesting, and that corresponds to the let's say, reconstruction part of the autoencoder, which is now, given the representation, I should be able to sample back here and produce a new configuration of my visible unit. So a new configuration, which was not the data configuration. It may be close to it, but that's something a priori different. Okay? And then if I just iterate that, then this sequence of extraction and reconstruction should actually allow me to sample the whole Gibbs distribution here. Is it clear? Okay. Okay, now, how is the machine trained? So, of course, we need to find the values of the different parameters. So there are many parameters for local fields, some defining parameters for the potential I will describe in a while, and obviously the connections, which are the very important parameters. So we have only data on the visible layer. So the idea is to compute the marginal, that is by integrating formally over the h mu's, we can compute, or let's say we can formally define some effective energy for the visible layer, where there will be some effective interaction between the visible units due to the integration over the hidden layer. And this P of V, which is the marginal, is the thing which should be maximized over the data. So that depends on all the parameters of the model here. So essentially, we can assume that all the data items are independent from each other. They were drawn from this machine, and we will maximize the product over all the data items of the P of V of this configuration. Okay. Okay, so this is unsupervised learning. So just to be a little bit more precise, and you will see a connection with Hebbian learning. So how do we do that? So we want to maximize the log of a P of VB. So B is the index of the configuration we have in our data set. So it goes from 1 to capital B, the total number of data configurations, which depends on the WI mu, the connection, which depends on the GIs, and so the parameters which define the effective potential the potential on the hidden units. So for any parameter here, this is done by gradient ascent. Essentially, what you want to do is to differentiate the log P with respect to theta. And if we look at that, you see that in P of V, let me do that here. So PV is the integral over H of P of VH. Okay? So we want to maximize this thing here. So it has some term, which is the exponential of minus the effective energy of V over Z. Now, and all these things depends on the parameters, the theta, obviously. So if I have log of P of V, this is simply minus the effective energy of V and theta minus log Z. Okay, and then if I compute the derivative, there will be two contributions, one coming from this one and the other one here. Okay. Now, if you look at the, let's suppose, for instance, theta is the weight, the connection between I and mu, just as an example. So when I differentiate this energy here with respect to Wi mu, what will happen? What I will find is the VIH mu product. So that will mean if I choose this thing here and I differentiate, I will get a term which is VIH mu. And then if I sum over, but this H mu obviously is integrated here over this measure. Okay? So I will have, when I compute the sum over the data items, which is here, I will have a double average. I will have an average over the data, which are configuration of the V's. But H mu here will be average also, so that's another average. So that corresponds to the average value of hidden unit mu when I present configuration V on the visible layer. And that should be average of the data. Okay? And then there will be a term which has exactly the same structure here. But this term here, if you think about it, this is simply some kind of average here, VIH mu, when you average over the machine. So P, there is a joint distribution for V and H. And so VIH mu for given values of parameters has the well-defined values. And when you differentiate this thing with respect to Wi mu, you get this. So essentially saying that we want to optimize P of V with respect to Wi mu means that we want that the correlation between hidden and visible units computed from the data should match exactly the same correlation computed from the machine. Okay? So it's a matching condition. It's a moment matching condition. But it's somewhat similar to Hebbian learning to some extent, because here you see that since we do gradient ascent, what we would like to do is actually to update the weights, for instance, at time t+1, so where t is the learning time, as let's say the difference between the weight at time t+1 and the weight at time t should be proportional to the gradient, so that we can climb up the gradient. So you have a positive proportionality coefficient in front of that. So this is very similar to the Hebbian learning rule I mentioned in the previous lectures. Except that, so this is the same thing here in the data, except that this term here usually is much simpler. So that's a very complicated function of a W here. Very hard to compute. Well, usually in Hebbian learning, remember in Oja's rule, we just had something which was proportional to the weights, which was a saturation condition for the weights. So usually in Hebbian learning, we have very simple functions here. This one in RBM is very complicated. So that's the major difficulty. And how this is computed? This is just computed by Monte Carlo Markov chain sampling. So it's just an approximation. So what you can do is exactly use the sampling procedure I presented before and approximate this and compute some approximated value of that. Is it clear? So this algorithm is called contrastive divergence. It was introduced by Hinton and collaborators some years ago. But it's a extension of Boxful machine learning, which dates back from the 80s. Okay, so as I said, these machines were introduced in the 80s, and nobody did anything with them for a long time. And then the situation changes about 10 years ago, a bit more than that, with this paper by Hinton and Salat-Tudinov. So this paper essentially showed that, so it's an interesting paper because it mixes autoencoders and RBM. So the use of RBM was somewhat marginal in the paper. So basically what these people say is that if you want to do better than PCA, you can use autoencoders, as I tried to convince you about in the previous last week. And they had complex autoencoders with different layers. So you see layers here of different sizes. So it was not a single input layer and then a single hidden layer and then the output layer, but you had more than one hidden layers here. And one major problem when you have this kind of machine, So it's easy to write down the cost function, as I did in the first slide, right? Except that when you want to do learning of that, you have to minimize this cost function, and there are a lot of derivatives coming from all the weights here, and it's very hard actually to find a good local minimum of this cost function. So you need a very good starting point, a good guess of the W's in order to achieve good performance. So the idea that Hinton and Salatudinov had was to do some kind of pre-training of the weights, and they use RBM to do that. So they use RBM. First, just with this unsupervised training scheme I've just shown, you can have your visible configuration here, your data. Then this is the first hidden layer of the autoencoder can be seen as the output layer of the RBM. So you do some pre-training here, so you compute the W1. Then you can see how, once you get the configuration here corresponding to your data, then you can see how to train another RBM between this layer and the second hidden layer and so on. So you do this pre-training, layers by layers, like that. Then you can combine all the weights here, and that will be some kind of initial condition for the training of a total big autoencoder. So RBM came back to life, let's say, about 10 years ago to pre-train deep networks. But then people were able actually to do some kind of training in a more efficient way, and they were also a little bit less used compared to deep architectures. Okay, so this paper was very influential in the field. So let me show you now what you get when you use a single RBM, so very simple architecture, only 2 layers. On the data I have already mentioned, which are very used data in machine learning, the NList data set, just to give you an idea. So that was done by many people. Okay, so let me, of course, I have to specify here a lot of things. So I have to specify in particular the hidden unit potential, which is U of H. Okay, so I will tell you a little bit how we choose U of H. So let me give you just the value of U of H here, and I will justify why we do that. So that's something that a lot of people do. So U of H here is chosen to be a potential with a hard wall on negative H, and to be a quadratic function with some finite slope at the origin for positive H. So there will be some slope here, theta h at the beginning, and then some quadratic growth like h squared. Okay? So I will explain to you later why this potential is used by people in the field. Okay, so you have a large number of images, which are 28 by 28 pixels images. And now you can do the training exactly with the algorithm I showed you. And this is what you get, for instance, for this machine. So let me see if I can. Yes. So what you will see here are, so you see 10 different Markov chains simulations. So the training is done. I'll talk about the training a little bit later on. But let's say training is done. And what you get here is 10 examples. They are just independent simulation with this, sampling the visible layer, hidden layer, visible layer, and so on, starting from different initial conditions. But this is exactly 10 times the same machine. Okay. So what you see is that, for instance, if you focus on one particular simulation here, you see the sampling here of different digits. So some digits look nice, so the configurations are less nice. But you see that the same machine is able actually to sample a lot of diverse configurations. Okay? So this is a machine with a single layer. Nothing is deep here. Okay? So the size of the machine I did not mention. So this is 400 hidden units, while the total number of visible units here is 28 by 28, which is a bit less than 800. Okay?
Sorry, just one question.
Yes.
If you sample, you get a number, and then at some point it changes from one number to the other.
Yes.
So the change is very rapid, or it's
The mixing?
yeah.
Yeah. Okay. So okay. I don't want to say too much about that, but in fact, yes, you will see it's much faster than for Boltzmann machine. So maybe I can show you some slide about that. I can include at the end. Yes, so it's a very important thing, and there are some deep reasons for that. Well, it's actually mixing much faster than Boltzmann machines. Yes.
N is the number of hidden units. No?
Yes.
And can I ask why? Here in the list, I guess that there are 10 classes more or less. So
yes.
I would expect to use an M that is of order maybe 10, but...
No, okay, so maybe I was, what I said was confusing. Most people, when they use MNIST, do that to train classifiers. They want a machine which is able to say, oh, this is a 10, or this, oh, no, what? This is a 9, or this is a 0, or this is a 2, okay? Here, this is not what we are doing. Here, I want a machine which is able to generate new digits, okay? So it's an unsupervised learning of the distribution of these numbers. And the machine is actually running, and it just creates new digits. It's not telling me whether it's a 4 or 0 or whatever. We could build a classifier on that. Actually, if you have your machine when it's trained, a classifier on the hidden representation will be much more efficient than the classifier on the visible units, because a lot of job is already done in the representation to separate the different digits. Okay? If you do that with 10 hidden units, then the quality will be very, very low. You will have very poor approximation of the digits. So we'll see how the quality changes with the number of hidden units. Okay, so why this potential and not something else? So that we can understand a little bit from the sampling. Remember what I showed in previous slides. When we do sampling, we have, if I fix the visible configuration here at time t, in the sampling, I will sample the values of the hidden units here from this distribution, where I mu is the input to hidden unit mu, okay? So let me see, for instance, what is the most likely value of h mu given the inputs here? Then I have to find the maximum of this distribution, right? So the maximum is given by the point where the derivative of u is equal to the input, right? And this is this is a scalar relationship. So implicitly, that defines h as a function of the input. I just have to invert the u prime, right? So now, what kind of function do we want here? So this is telling me what is the activity of the hidden unit as a function of the input it receives. So what are the interesting functions you can think of? The simplest function you can think of is h proportional to I. Okay? So h would be a linear function of I. So what does that mean? If phi is the identity, the slope does not matter here. That means that actually the derivative of u is the identity. So u of h is actually h squared over 2. So the linear case, so linear phi, that corresponds to u of h equal to h squared. Okay? Now, is it a good idea to have a linear transfer function here? Actually, it's not, and that has been known for a long time in machine learning. Empirically, this is not good, and the reason is the following. If you think a little bit about what this thing is doing, so what is doing h here? When we sample back from the h's to find a new configuration, d here, h is actually, as I said different times, is actually telling me how much the feature w mu is present in the data. Okay? Now, there are two possibilities. Either the input is very strong, and that probably is a signal. That means that the configuration v is actually, if I think of the n-dimensional space, somewhat parallel, or let's say has a large dot product with the feature w mu. And probably this is a signal which is important. So in that case, I want the activation h, the activity of the hidden units, to be large, because I will use this signal to reconstruct a new configuration where w mu is also very strong. Okay? But now, if I is very small, close to 0, actually it does not matter. Maybe this is just pure noise. So in order to clean this out, it's much better to have h equal to 0 than to have h small. Why? You may think that h small actually does not matter too much. This is true if you have a single hidden unit. If you have plenty of them, and many have small noisy values, when you sample back the visible units from this very noisy hidden configuration, then a disaster will happen, and this is what is known in the Hoffa Model as the blackout catastrophe. I mean, I will see the connection with the critical capacity of the Hoffa Model. Okay. So this is a very good idea when you have a small input here to put h equal to 0, and this is correspond to the idea of introducing some threshold theta here. Okay. So instead of having something linear, it's much better to have 0 if we are below some threshold. Now, what about the asymmetry here? Another constraint you may add, but this is not necessary, is to say, okay, if I have a feature, it makes sense to ask how much this is present, how strongly this is present in the data, and you would expect this number, this degree of presence, to be a positive number. It doesn't make much sense to have a negative number of presence of some feature. So this is why people in the field consider rectified linear units, which are 0 up to some threshold theta, which is positive, and then which increases linearly with I. Okay, but this is not a necessary condition. You could have a double rectified linear units with also a negative part if a sign actually matters. Okay. You could have also different units, like Bernoulli units, which take only 0, 1 values, and this is a different choice of potential. So now the fact is that if you want to realize this transfer function here, then that corresponds to this potential. Okay? A hard wall to prevent h from being negative, then a slope here, and then a quadratic increase, which corresponds to this linear part here. So I said that these rectified linear units actually give better results than the linear ones. So let me show you this. So what you have seen here is this simulation. This is the same as the one I showed before. Now let me show you what happens if you take now a purely quadratic potential, u of h equal to h squared, and then you do exactly the same algorithm, the same training and so on. So what you see here are two things. First of all, most of it, well, I mean, some digits may be well formed, but actually in many cases, the digits don't look as nice as here. And the other thing you can see is that actually the dynamics is much lower and can get stuck here. And for those of you, well, not so many of you have my age, but I mean, maybe. Then if you remember the old things from the Hoffa model from the 80s, this is typically what people had. And in fact, this model is exactly the Hoffa model. So I'm going to explain that now. Okay, so you see, you can get stuck in what people call spurious states of things which are some kind of strange mixture of digits and have absolutely no meaning, or you can get a lot of defects in the images which are formed and very slow dynamics. Okay, so if we choose u of h equal to h squared, this is the Hoffa model. So why? So this is very simple to see. So remember the energy function. So this is the sum of the local field, local term on the visible units, the potential acting on the hidden units, and the coupling terms. So now if I write the joint distribution, it's just the Boltzmann term here. And if I compute the marginal, then I have to integrate over the h's, right, to get the effective energy on the visible units. Now in the particular case where u of h is a squared of 2, then this integral is a purely Gaussian integral. So this is very easy to do. In fact, it's a very simple Gaussian integral because all hidden units are decoupled from each other. Okay? So obviously what we get in this effective energy here is the local term, which is not affected by the integration, plus what? Plus this linear term here, which is squared. So if I expand this, I get a sum over I and j, so all pairs of visible units. And then the vi vj, and then I get an effective interaction between the visible units here, which is sum over mu of wi mu wj mu. And this is exactly the Hoffa model, right? So in fact, this is another representation of a Hoffa model, where usually we write the Hoffa model at the model with some couplings here between the units, and jij would be the sum over mu of wi mu wj mu. And here the representation with RBM is somewhat different. We have hidden units which correspond to the different patterns. So this is pattern mu here, so mu equal 1, for instance, and mu equal m, the last one, and so on. But this is exactly the same model when you have a quadratic potential u of h acting on the hidden units. So that means first another thing, that means also that if u of h is not Gaussian, then the effective interaction term here will be more than pairwise, will include more than pairwise interaction. Okay? So that's an interesting thing because I'll come back to that later on in the application after the break. But a general problem when we analyze data is that pairwise interaction may be nice, but they are not sufficient to represent the data in many cases. So we like models with higher order interactions, but the problem is that the higher the order, the higher the number of interactions. Obviously, that grows exponentially with bigger. And so there are not so many data that you can infer a lot of very high order terms, couplings. So RBM are a way to introduce effectively let's say in a parsimonious way, higher order interaction. But they are not independent from each other, because they are all created from the same connection here. Okay, so this basically is what I wanted to say. In the RBI, essentially, you want to explain maybe some correlation you see in the data by the idea that actually these different visible units may be subject to different common inputs, which is an idea coming from computational neuroscience. And you see that in the specific case here, what you get is a model where you explain the correlation through some effective interaction. That's typically what we do in physics, and we're much less accustomed to that. But these models are equivalent in this particular case. So just a word about the Hoffa model. So I don't know if all of you are familiar with the Hoffa model on the phase diagram. Okay, so the Hoffa model, which is exactly this model, was studied a long time ago, introduced in 1982 by John Hoffa. And the phase diagram of the Hoffa model, when you have random WI mu's here, was computed a long time ago in this famous paper by Amit and Sampolinsky. And so I don't want to explain the details of the calculation. The techniques were based on replica approach, very similar to the things I explained last time. So this is the phase diagram in the temperature alpha plane. So temperature is the usual temperature. This is the Hamiltonian, and you can sample from this from the corresponding Gibbs distribution with the temperature T. Okay, so let's say each configuration VI of the VIs will have probability proportional to exponential minus E over T. And alpha here is the ratio between the number of patterns, this W and mu, and the number of units. Okay, so in the Hoffa model, that corresponds to this sum here runs from 1 to alpha n. So that means that you have n units. It's a model over n units. And the interaction matrix between the elements is essentially of rank alpha n. If you prefer, in this formulation, that means that you have n visible units, and the number of hidden units is alpha n. So this is the aspect ratio of the machine. How wide is the hidden layer compared to the visible one? So when n goes to infinity, there is a well-defined phase diagram which includes different phases. At high temperature, you have a parametric phase where the so this was derived in the case where the GIs are equal to 0 and the VIs are plus or minus 1. But this is okay. So let's say the variables are essentially not correlated to each other. So not very interesting for us. So let's look at the low temperature phase diagram. There are two phases. One is the ferromantic phase, one is the spin glass phase. And maybe this can be understood in the best way in the following diagram here, which is extracted from the same paper. So you may ask the following thing. So this model was introduced as a model for memories, auto-associative memories. So the motivation was coming from computational neuroscience. So let me assume I start my configuration VIs from one of the patterns. So for instance, the VI at time t equals 0 is equal to WI for mu equal 1, for instance. Whatever mu, I mean, choose the mu as you want, but let's say mu equal 1. Now you may ask, you may actually run some kind of Glauber dynamics, Monte Carlo dynamics on that, and ask what is going to happen for the long time dynamics. Especially, for instance, if I am at 0 temperature, then the system will converge to a fixed point, right? And the question is, how similar is the fixed point to this particular pattern, okay, to this particular state of activity? So if the similarity is very large, that means you have been able to actually embed in the interaction matrix one particular desired state of activity, one fixed point of the dynamics. So this is actually how you can build a memory. If the final state has nothing to do, then it's a failure. That means there are so many maybe patterns or whatever that it's very hard actually to encode in the hard way some particular state of activity. And whether this is possible or not depends on alpha. And here what you see is the fraction of the bits at the end at a long time when you reach a fixed point, of the bits of the fixed point which are different from their values in the pattern. And you see this fraction is very small as you increase alpha. And then when you reach alpha very close to 0.14, it jumps from let's say 1.5% to 50% when alpha crosses a critical value. That's called the critical capacity. Okay? So that means that above this critical capacity here, essentially there is no way, the fixed point of the dynamics have nothing to do, the local minima of the energy have nothing to do with the patterns. Okay? And the reason is that there are so many W's in this sum here that actually there are a lot of interferences and you cannot memorize anything. So how can we find back the same thing in this architecture? So I'm just trying to translate what was known for 30 years in this architecture here. Okay, it's just rewriting the same thing. Well, it's very similar, but you will see exactly why actually having a non-quadratic potential is a good idea. So let me assume now that I start exactly from a state of activity on the visible units, which is exactly the WI1, for instance. So if I am in 0, 1 spins, I can choose VI equal 1 if WI1, this is the first hidden unit, is positive, or 0 otherwise. Otherwise, I can choose, if it's plus minus 1, the sign of WI1. Okay? So this is my visible configuration. Now I sample the hidden unit configuration from that. So if I look at this hidden unit here, then what is going to happen? This one will receive an input which is extremely strong, right? Why? Because all the weights are compatible with the state of activity of the corresponding visible unit. So if I have a linear machine, the input will be equal to the activity, phi is the identity. So I just have to sum over I, WI1, VI, and this is very large. Okay? Essentially, this is of the order, this is proportional to M times the strength of the W. This is the order of magnitude of this activation. So very strong activation here. What about another hidden unit? If I take another hidden unit, whatever mu which is different from 1, if I assume that Wi, mu are independent from each other for different mu's, then of course when you see that when you sum these things, I have n terms, but since the Wi mu and the Vi are uncorrelated to each other, then the order of magnitude of this term here will be of the order of square root of n, not n. So they are all weak compared to this very strong one. Now, once I have determined the configuration of hidden unit variables here, I can sample back and see what happens, for instance, on visible unit I here, and see what is the field, the effective field that this visible unit is receiving. So it will receive a very strong activation coming from this one, which is order n, weighted by W. This one, WI1. So n times something, order W squared, plus very small compared to this n, so square root of n activations, but from many hidden units. So how many of them? Well, order m, okay, so sorry, it's a p here. But I mean, and essentially the number, the order of magnitude of this noise term will be the square root of n times the square root of m here, since they are all independent and uncorrelated with each other. So as long as m is much smaller than n, this term here is much weaker than this one. And that means that if I started from this initial condition here, I will sample back exactly the same thing. And I am in a very good shape. And that corresponds to this part of the phase diagram of the Hoffa model. I am deep here in this phase. While if m becomes of the order of n, so here p, okay, then this term may be of the same order as this one, and then the situation becomes complicated, and that corresponds to the critical capacity if you are above some threshold. Okay, so that's the usual way one is taught about the Hoffa model, I think. Okay, usually that you see the single term and the noise term. But actually you see that if I, instead of using a linear transfer function that is a quadratic potential, I choose something like that, okay, then I will get a much better result, because a lot of hidden units here will be silent. Because if they are below the threshold theta, if I choose theta of the order square root of n, I will kill a lot of activity here, and all these zeros here will transmit no interference, no noise here. So that means that I can increase a lot the number of hidden units, so I can go to much larger values of alpha. And this is the same idea as what I wanted to explain to you in the previous weeks about sparse autoencoders. It's good to have very large hidden layers, which is alpha, that's the aspect ratio here. And you can do that because you want to do that because you have more features you can detect. But in order to do that, you have to put a strong sparsity condition in the activation. And this is exactly what people have been doing in machine learning for a long time. but I think which was not understood for a long time also in statistical mechanics in the context of a Hoffa model. Okay? Okay. So essentially, if I want to summarize, the phase diagram found by Amy, Gufons, and Polinsky can be summarized, or let's say just rewritten, in the context of RBM. The fact that at very low temperature, you have two phases, either ferromagnetic phase, where if you sample from this machine, you will have configurations V's which match very closely one particular set of weights. So one hidden unit will be very strongly activated, and the other one will be only weakly activated or silent. And if you increase too much alpha, that is, you have a too big, so your hidden layer is too big, then you get into the glassy phase where the visible configuration will be uncorrelated with the weights. Okay? So all this activation will be weak. Okay, so now some questions I would like to address before the break. So one question we may ask actually, how is such a machine capable of generating good data? For instance, what you saw on the MNIST example. So what is the role of the nonlinearities? So we have already talked a little bit about that. And say how the phase diagram of the Hoffa model is actually modified when you have nonlinear hidden units. Okay, so just a little bit of phenomenology. And you see this is essentially what we have already seen in autoencoders in the last lecture. So what kind of things do we see at the end of the learning? So here what I'm looking at is the receptive fields of the different hidden units. Okay, so after the learning. So you have 400 hidden units in the example I've shown. And each image here, for 6 of them, is the set of weights. So they are represented by a 28 by 28 images, okay? And these weights are real numbers. They can be positive, red column, negative, blue, and they can be close to 0, white column, okay? So what you see are actually a set of weights which are very similar, look at this one, to the feature detectors I mentioned last week that you find with autoencoders, but you find also with sparse distributed learning, and you find with Hebbian learning, and you find also in the V1 of the monkeys, all these kind of things I mentioned last week, okay? So a lot of weights are actually very close to 0, and you get strong positive and strong negative weights, which compute effectively some kind of local contrast here in the visible layer. So once you see that, you may ask, okay, so how do I build a digit from these kind of things here, okay? Because if I present a digit, this digit, okay, will activate some of the hidden units. You have to compute the dot product between this and this to see whether the corresponding hidden unit will be activated or not. Another question is, what kind of representation do you get in the hidden layer? So first, one thing you see is that if you look at the conditional average during the sampling phase after the learning, this is the conditional average for one particular representation at equilibrium in the hidden layer. You see that the effective temperature of the machine is actually very low. Because, so by conditional average, I mean you fix the H's and you sample the VI's. The VI's are 0 1s, so you can compute the average value of each VI. So it's a number between 0 and 1. And you see that most of the pixels are either 0, black, or 1, or very close to 0, very close to 1, and there are only a few of them, especially on the boundaries here, on the edges of the digits, which are somewhat have a magnetization different from 0 and 1. That means that the effective temperature is very low. And in fact, you want that. A well-formed digit should not have, white pixel blinking all over the place, right? So that means that the training was good. So that means that we have a lot of weights which are equal to 0 here, or very close to 0, and the remaining weights are actually very strong. Okay, so just a little bit more of phenomenology, and you see that again we find always the same phenomenology as in the sparse autoencoders. There is nothing very new here. So these are different digits which are, okay, so if we look for instance at when you generate data from the equilibrium distribution of this machine, you may ask, okay, how is formed the representation layer, configuration activities. So for instance, we can compute how many hidden units at any time are silent. So it's a number between 0 and 400. And this is the histogram. So you see that there are about 250 hidden units which are silent, so below threshold. So it's, sparse activity, in the sense that more than half are just silent. Not always the same, obviously, otherwise they would be disconnected from the machine. I mean, it depends on the particular configuration on the visible layer. And now we can have a proxy for the very strongly activated hidden units. So L will be computed from some kind of inverse participation ratio. So what you can do, for instance, is to compute, the sum of a mu, h mu to the 4, over the sum of a mu, h mu squared. Okay? This kind of inverse participation ratio you may be familiar with. So if all the h mu's are equal, or the same order of magnitude, that basically gives you 1 over the number, so the number of hidden units, 1 over m. So the inverse of that will tell you how many hidden units are strongly activated. Okay? And if only a few of them are strongly activated, so most h mu are close to 0 except a few n, that will be that will give you this number. So it's a proxy. The inverse of this ratio is a proxy for the number of strongly activated hidden units. And you see that about 20 of them are strongly activated. So what that means that each visible configuration here is built from the activation, the strong activation of about 20 features. So you define local patches, and the combination of these patches is actually building some digit. And you have a sea of weakly activating things and a lot of silent ones. Okay? So this is a sparse encoding. Okay, so let me see. I don't know whether I should stop here or. So we have seen that having nonlinear transfer function can be very useful for the encoding of the different inputs here. So one of the questions we'd like to ask is, what is going to happen to the Hoffa Model phase diagram? How the nonlinearity is going to affect or not the phase diagram? That is the question. So in order to do that, we can just repeat the calculation which were done 30 years ago in this context here. So again, so what is the model? So the model is very similar. Remember how the Hoffa model can be translated here into a RBM. So we have the patterns. The patterns are the connection between the visible and the hidden units. They will be considered to be random. So usually in the Hoffa model, they are random plus or minus 1, for instance. And alpha is the ratio between the number of patterns and the number of visible units. So this is the aspect ratio of the machine. So two differences with respect to Hoffa model in the model I'm considering here. First difference, now there is a potential here acting on the hidden units, which is not a quadratic potential. That's a potential which is the rectified linear unit potential, that's this one. Okay, where theta is some threshold. So this is the first major difference. Second difference, as we've seen, if you look at that from this purely phenomenological aspect, it seems that a lot of the weights are actually equal to 0. We are not in a situation where we have half negative weights, half positive weights. But actually, if we want to be more realistic, we need another parameter which actually tells us how sparse are the weights here. So we'll have a model where we assume that a fraction p of the weights, where p is a number between 0 and 1, are non-zero, and they will be plus 1 or minus 1 with probability 1/2. And a fraction 1 of minus p of the weights are equal to 0. Okay? So it's another extra parameter, which is how sparse is the machine. And this is a crucial parameter. Okay, so we can repeat the calculation, and again, what we want to do is to compute the partition function on this model. So the partition function of the model will be the integral over the h's, the h configuration, the sum over the v configuration of the Boltzmann weight, where the energy is the sum of all these terms, the local potential acting on all the units plus the connection term. And we want to do that in the limit where n is going to infinity. In theory, also, we would like to compute this as a function of temperature. That can be done. But as we have seen, we are interested in the phenomenology at very low temperature. So let's compute first what is going to happen at 0 temperature. And this is going to give us a free energy, which will depend on the different parameters of the model, which is alpha, p, the sparsity parameter, theta, the threshold here, where I'm assuming all the thresholds of the hidden units are equal, and also this local field acting on the visible units. So I won't do the calculation on the blackboard because I think it's a little bit boring, and it's exactly the same kind of technique I've already explained once. So you can do this calculation. If you're interested, I can give you some references. Okay, so this is the free energy. So I just want to comment a little bit about the formula, because I think there are interesting things about formula. So you see different contribution in the formula. Okay, so this contribution actually can be associated to the different pieces of the machine. So one contribution, the orange one, is actually telling us something about what is going on in the visible layer. So this is, okay, so in the visible layer, and that depends on some other parameters, which are this B and this R here. And we have another contribution which is proportional to alpha and depends on the effective potential here, U of H, while this one was depending on G, and that is related to what is going on in the hidden layer. Okay? And then we have an extra piece which is telling us how the two layers are communicated between each other. So the other parameter R and Q, so Q is the same order parameter as usual. This is the overlap between the visible configuration. R is another parameter telling us about the magnetization of the, let's say, not so much active hidden units. And B and C are response functions. Tell us if I change a little bit the activity in this visible unit here, how will it change the average activity of these hidden units, and vice versa. So we have B and C, which are two response functions. Okay, and M here is the activity, the magnetization of the very strongly activated hidden units that we expect to find in the ferromagnetic phase as we had in the Hoffa model. Okay, so and the whole thing should be optimized over everything. Okay, and L here is the number of strongly activated hidden units. So there are all other parameters which should be found by extremizing F. So when you do that, you find actually the same phases as before. The ferromagnetic phase where a single hidden unit is very strongly magnetized, or none of them are magnetized, which correspond to the ferromagnetic and glassy phases that were present in the Hoffa model. But as P is decreasing, that is, as the weights become sparser and sparser, there is another phase which is found, where actually a large number of hidden units is are strongly magnetized. And this number scales as 1 over P, where P is the sparsity. So remember, we have two limits here. One is the size of the machine, n and alpha n, the two sizes of the layers. N goes to infinity. And then you have a sparsity parameter P, and you can send that to 0 next. So it's you have to be careful with the orders of the limit of the limits. But essentially what we find here is that a large number of these hidden units can be magnetized. Okay, so how does that work? So again, I would like to reproduce the argument I've shown before. Remember the argument I've shown for the Hoffa model? So I just want to see how this is modified in this phase. So that was exactly what I had. Remember, we assume we start with the visible unit, which is a line along the corresponding waves. The magnetization is very strong here. We have a lot of small magnetization, but when we sample back, this noise term may be comparable to this signal term. So what is going on now when we have non-linearities? Well, we can kill the activity of these weakly magnetized hidden units if we put a threshold theta, which is comparable to the average activation here, to the typical activation. So if theta is order square root of n, then these ones will be silent. So if they are silent, that means they will not give this noisy contribution here, so we'll get a much stronger activation here. Okay? So that helps a lot. And essentially, what we have now is that the number of hidden units which are strongly magnetized is not 1, but it's something which scales as 1 over P with some factor here, which is a non-trivial factor, which has to be found by minimizing the free energy. And this thing here will determine the activation here. So you have a certain number of features which are strongly activated here, and the composition of this pixel, the value of this pixel, will depend on these different activations. So that means in the same visible configuration, you may have different features which are activated. So it's a mixture of patterns now which are activated. So the idea of having mixture of patterns activated was also present in the Hoffa model. That is possible, actually. And if you look at the very nice book, old book by Daniel Amit on attractor neural networks, I don't know if you know the book, okay, where so he talks about these spurious patterns, spurious states of activity. And there are two facts that should be said about these things here. So essentially, you ask whether you have different vectors wi mu, and you ask what are the fixed point configuration of the Hamiltonian, and you compute the magnetization mu, which is the sum of I sigma I wi mu, and the question is whether this thing is order 1 or it's 1 over square root of n, so 0. Okay. So usually, and you ask what is going to happen to the free energy as the number of mu's which are order 1, which I call L, is increasing. And what happens as a function of L is that the free energy of this phase is increasing with L. That means it's possible to find fixed points which have overlaps on 3 patterns, for instance, but the free energy of these phases is very high. So you will typically not find them, okay? It's just irrelevant. And in fact, in his book, Daniel Amit says that he thinks that these spurious states are really spurious. They don't mean anything. They are not interesting. So the fact is that if you have sparsity, then what is going to happen is that these different patterns now do not compete exactly on the same sites, on the same visible units. So they can basically be next to each other and combine to form a complete visible configuration, which is interesting and has some meaning. And in fact, what happens is that, I want to show that here, now, instead of being an increasing function of L, the free energy can be non-monotonous in L. And that's the main difference. So you can have something which is like that. Okay? And that will select a specific value of L here, which is a non-trivial function. Okay? That never happens if you don't have any sparsity in the patterns. So I'm coming back to that. So one prediction of theory is that the number of hidden units which are strongly activated, L, should scale as 1 over the sparsity. And in fact, that can be seen if you train again the machine on NList or any kind of data, but I mean on NList here. I will show you also on proteins in a while. So how do you change P? So you can change P by increasing, for instance, the regularization penalty, so that you will get higher penalties for large weights, and that pushes the weights to be equal to 0. So you can see that as P decreases, the number of very strongly activated hidden units is basically growing as 1 over P. And this is obvious, I mean, because if the features that each hidden unit is coding for is shrinking, since the data are not changing, the only way you can compensate for this shrinking is to have more hidden units coding for the same data. And that should scale as 1 over P. So there is nothing surprising here. But you can see that in the data. Okay, and so now we see a competition between, let's say, different phases. So this is what happens as you increase, for instance, for certain values of alpha, the threshold theta, and so on. You increase the parameter G here. So what you see is that, so this free energy as a function of L, more precisely L over P. So that tells you how the number of very strongly magnetized hidden units is scaling as 1 over sparsity parameter. So if you are in this region of very strong negative G, for instance, so a lot of pixels will be equal to 0, or you have a lot of DIs equal to 0, and then you maybe in the Hoffa phase, ferromagnetic phase here, which is a monotonically increasing function of L. So this is the free energy here. This line here is the free energy of a spin glass phase. As you increase the weight here, the field, sorry, more pixel can be +1 instead of being 0, so there is more variety in the visible configuration. And you can see a non-monotonic behavior here with some well-defined value of L, which is selected. So we are in this kind of compositional phase with a lot of hidden units which are activated. And as you increase the gain, then you have more and more 0 and 1s. It's kind of mixture, and then that will favor the spin glass phase, for instance. Or you could increase also alpha or decrease theta, and then at some point the free energy of a spin glass phase will win over the other one. So it's essentially the same phases as in the Hoffa model, except that you get, on top of that, this new phase with more than one hidden unit which is strongly activated. Okay? And in fact, this kind of phase transition was empirically known in the machine learning community. So this is extracting from one paper 4 years ago, Fisher and Nigel, which is some kind of reference paper on practical training of RBM. So again, that was on MNIST. And what they have seen is that they have, so they are not rectified linear units, but they are Bernoulli hidden units. So the hidden units can take 0, 1 values, but it doesn't change so much for what I'm going to say. So what they have done is that they have again used this same MNIST data set, remember 28 by 28 pixels figures, and they have done the training with 2 different kind of RBMs where they change the number M of hidden units. So either you have 16 here or you have 100. And after the training, these are the weights you see. So it's a gray color code. It's not it's a gray, not a color code as before. You remember red on blue, but this is the same thing. So strong. The dark points correspond to positive couplings, and the white ones to negative ones, I think, and the gray to essentially 0. So you see, when we have a large of number of hidden units, you get very sparse features here. While if you are in this situation here, you get features which are not so many of them, of course, 16, and they basically code for prototypes of the numbers. Okay? So essentially, we are in a situation which is very close to the Feynman phase of a Hoffa model, where you have patterns, and you can create visible configuration which look like the patterns. So there will be some kind of finite temperature excitation around that, and this is all what you can do. While here, it's a completely different behavior. There are many small local patches which can be combined, and many of them can be combined in order to produce a large variety of visible configuration. Okay? And this is possible by, this is made possible by the sparsity of the weights and also by the non-linearity in the units. Okay, so now in the last 40 minutes or whatever, I'd like to talk about some practical application of that and see whether we find also these different phases when we try to actually address real data. And I will do that on proteins, the analysis of protein sequences, which is a very active field right now, which has been for a long time. But I mean, it has been renewed a lot over the last 10 years. Okay? So I don't know how you are familiar with this field. Maybe some of you know, or maybe other ones don't, so I will be very introductory here. So, so I've been interested in proteins in the last, let's say, 45 minutes. So proteins, from a purely chemical point of view, they are just polymers, or let's say heteropolymers of amino acids, peptidic chains. And the protein is, so this is the, let's say, primary representation of proteins, which is just a sequence of amino acids. So there are 20 natural amino acids. Yeah. And this chain of amino acids may fold in most proteins, in many proteins, in a well-defined 3D structure. This is some kind of representation 3D structure. Here, this is actually a small protein, which is called a protein domain, a WW, which is an important binding domain of proteins, which is binding units. This is how a larger protein will include this. So a larger protein will include these small protein domains in order to be able to interact specifically with other proteins, okay, or with other peptidic chains. Okay, so this chain will acquire some 3D fold and will have some specificities. That is, it will be able to bind some peptides in a specific ways. That is, some peptide will bind, other one will not. So one question which has been very important in the field for decades is how is the structural information and the functional information encoded in the sequence? It's a major question. Can you predict that from the knowledge of a sequence alone? Can you understand what are the determinants in the sequence of the function and the structure? So this is this is one example of a very important problem, which is called the genotype-phenotype mapping in biology. How you understand the function, the features, the characteristic of your system from the microscopic knowledge of its constituents. And in fact, changing one amino acid, for instance, along the sequence can have dramatic consequences. So along most sites, when you make a mutation, maybe nothing will happen, okay, in let's say standard conditions. And the protein will still have a nice function, a nice structure, and everything will be nice. But along some position, and for specific mutation, then you can have very strongly detrimental effects. And maybe the whole structure will break apart, okay, and the protein will not be functional at all anymore. So this is very important to understand how mutations affect the stability, thermodynamical stability, which actually determines how the structure, the folded state competes with the unfolded state. The activity, how much this protein is able to bind a ligand, the specificity, what kind of ligands it will bind to, and many other aspects or functional aspects. And this is important for fundamental biology to understand how these proteins have been evolving and so on, but also for practical application, where people actually want to improve the activity of proteins to design drugs, specific drugs, and so on. An important fact also, which has been well known for a long time, is that mutations are not independent along the chain. That is, the effect of one mutation here and the effect on another mutation here may be known, but when you do both the mutation at the same time together, then the effect may be very different for the sum of the two effects. So there are very strong interaction among sites here, and this is a property called epistasis in the field. So there are many different ways of trying to try to understand these kind of things. For instance, one way, which is first principle approach, so you can essentially build some Hamiltonian at different levels of coarse graining, maybe all atoms or something higher level, trying to take into account all the interaction between the different components here and try to see how the protein will fall, for instance, and these kind of things. So these approaches have been successful for essentially short domains, and they have been very successful to find secondary structures, some motifs here. You see secondary structures, these beta sheets, for instance, antiparallel beta sheets here, alpha helices, or these kind of things, and the 3D fold of small domains, but it's very hard actually to predict the folds of much larger proteins. Okay? And this is still an open problem to many aspects. So one approach which has been actually introduced some years ago is, let's say, based on homology. So what is the idea? The idea is here, what you see here is, let's say, some kind of tree of life, phylogenetic tree. If you look at the organisms which are actually living right now, we are somewhere here, okay? So you may have eukaryotes, you may have archaea, bacteria, so many, a huge variety of organisms. And the basic prior we have on all these data, all these organisms, is that they have emerged from a last common ancestor, and they have diverged from it billions of years ago, okay? So that means that all the proteins we may find in living organisms now have evolved from the proteins of this last common ancestor. So for instance, if we look at proteins which have very fundamental functions, like cutting DNA, repairing DNA, which are needed in, binding to something, which are needed in all living organisms, we may think that actually they have all evolved from the same common ancestor. And of course, they have diverged a lot just by the fact that a lot of mutations may be neutral here. So the sequences are very different. Also, the environments of the organisms and the function have changed a little bit also, or maybe in some cases a lot. But essentially, what we can say is that maybe if we look at the proteins which have the same function, or essentially the same function in all these organisms, then we have many realization, many sequences of proteins with very similar function and structure. This is the idea. So you get basically a statistical realization, okay, of something which actually have common properties. And maybe from these statistical features of these sequences, we can actually understand how the information about structure and sequence and function is coded. So this is one example here. You have different sequences. This is how databases are made, public database, for instance, PFAM or UniProt. You have here, for instance, the name of the organisms where this protein was found or sequenced. And here you have the sequences that contains amino acids, and also another symbol, which is a gap symbol, due to the fact that not all proteins have the same length in the same family of similar proteins. So if you want to compare the different proteins, sequences, then you have to align them. And for instance, this one was shorter, so you introduce some missing symbols here, some gap symbols, in order to align and to compare to the other sequences. Okay, so for a long time, people have done that, and they have seen that on some positions are highly conserved. That is, they carry the same amino acids in all the known proteins, or essentially all known proteins, okay, having the same function. And in fact, these conserved positions are extremely important. So you see, for instance, the proline here in this third position. They are very important also to build this kind of data, this kind of format, okay? So they are used to align the different sequences. So where are these conserved positions? They may be in the protein core, so inside right inside the protein, okay, where changes or mutations are much more likely to disrupt the structure. Or they may be in functional sites, so on the boundary of the protein, the surface, where actually the content of the amino acid is very important for the specificity of a function. So if you change it, you will change specificity, so protein won't be functional anymore. But it has been also recognized over the last decade that some sites which look like neutral, for instance here, you see a lot of mutation seems to be possible. This neutral site actually not totally neutral in the sense that it's true that you can make mutation without apparently disturbing too much of proteins, but these mutations are not independent from each other. So what has been done, and these are ideas from the 90s, as soon as people have obtained a sufficient number of sequences in order to make some kind of statistics, is to try to compute pairwise correlations between the sites. So again, so what is the idea? You have your data, so many sequences of amino acids coming from different organisms. You can compute single point statistics on one side. What are the different frequencies of the different amino acids? Okay, so you get a vector of 20 or 21 frequencies because the gap is also there. Same thing on side J, but you can compute also joint frequencies, which is a joint probability of having on side I and J the amino acid A on I and B on J. And the correlation, or let's say the covariance matrix, would be simplyCijab, which is the difference between the 2 points and the product of the 1 point statistics. Okay? So you would expect if mutations are independent that this thing is on side I and J and it's essentially 0, otherwise it would be large, positive or negative, depending on the AAB. So just to give you an idea about the numbers, so the number of amino acids and the number of sites in a protein, that ranges from tens to hundreds. Okay? That's typically the number. So here I will show you some examples on small domains with 30, 50 amino acids, but you can have 200, 300 or more than that. Now if you want to compute this thing here, that means if you suppose you have 200, so the number of pairs of sites you have is 200 times 200 minus 1 over 2. Okay, that's a number. And then for each ij, you have to compute this thing here for 20 by 20 amino acids. Okay? So it's a huge number of parameters you have to infer or to compute from the data, and the data are essentially the number of sequences you have, and it depends on the particular family of proteins people look at, but it may range from a few thousand to a few tens of thousands, depending on how much this protein was studied and is present. Because the protein can be present more than once, also in different copies in the same organism. Okay? So just to give you numbers. So in the 90s, starting from this paper, people have looked at this very big matrix, okay, and they say, okay, let's see whether actually what is going to happen. Let's look for pairs of sites where it seems that the correlations are very strong. And what do they mean? So what you can do is you compute this matrix here from your data, so it's just an empirical version of the matrix, and in order to get rid of the amino acids content, just if you want to concentrate on the information about pairs of sites, you can compute some kind of Frobenius norm of this correlation matrix. That's the simplest thing you can do. People have more sophisticated version of that with mutual information, but it's not doesn't change anything. And so you have an index Fij, which is the sum of the AB ofCijab squared. Okay? It tells you how strongly the site I and J along the proteins are correlated. And the idea was very simple. It was that if you have a sequence of amino acids like that, which will fall in the 3D space, maybe sites which are very far away along the sequence will be close to each other in space. So you may imagine that if you have, for instance, a positively charged amino acid here, a negatively charged amino acid here, they get into contact. If you make a mutation of a negatively charged amino acid into a positively charged amino acid, that will disrupt the contact on the structure. So this is bad unless some compensatory mutation is done on the other side. And that will create strong correlation. So maybe proximity in space is responsible for strong correlations. So we could compare this thing here to the contact map on the 3D fold. And the idea was to rank the pairs of sites according to the score here and see whether the top score corresponds to the contacts on the 3D fold. It's a very nice idea. And this is what you get, for instance, one domain, which is a trypsin inhibitor. So the trypsin is a protease which actually digests and cleaves some peptidic chains. And the inhibitor is a protein which prevents the trypsin to act, okay, which is used which is an important thing in metabolism. Okay, so this is for this protein domain of 53 residues. What you see here are the top 30 Frobenius scores. So you take the top scores, and you build a link in between the corresponding sites on the 3D fold. The structure is known. And you put a red color if the distance between the corresponding amino acid with some criterion about the carbon atoms and so on. I mean, it's an arbitrary criterion, but if the distance is smaller than some number of angstrom, which is about 8 angstrom, I think, here, so it's not a very strong constraint. And you put green if they are far away from each other. And you see that you get a lot of big correlations which are actually correspond to amino acids which are far away from each other. So this idea was some kind of, it was very nice, very deep, but actually some kind of failure. And the thing stayed there for some years until people realized that actually we know in physics that strong correlation doesn't mean strong interaction, right? You may have, think of about a 1D interacting models. You may have strong correlation between two particles here, but they are not interacting directly. It's just mediated by other particles in between along the chain. So maybe this correlation matrix should be cleaned in order to have something which is more resembling interaction or statistical interaction rather than correlation. So this idea was the idea is that let's start from the same data, CIJB, and find a model where we had effective interaction between the sites here, which I call JIJAB, JIJAIAG, and see whether we can find some interactions here which reproduce this correlation. And let's do exactly the same things. When you have found this interaction, then just rank the top interactions, see whether they coincide in a better way with the contract map or not. So this idea was first proposed by Lapedes and collaborators in 2001 in this paper, which was never published, but that's a very good paper. And then it was found independently by Martin White and collaborators in 2009, and now it's a very important field. And so the idea was to say, okay, so you can do some kind of maximum entropy modeling, or base, if you want. I mean, it depends on how you want to present the framework. But essentially, let's assume that each sequence of protein has a probability P of A. So each sequence having a good function and structure has a probability P of A. And I will assume that this P of A is an exponential model where we have local terms, like local fields, but also pairwise interaction term. Okay? So if your sequence is of length L, that defines a probability distribution over 20 to the L sequences. And you can compute the Gij and the Gi, which reproduce the 1-point and the 2-point statistics in the data. It's just moment matching. So it's very similar to what I have shown before. But now it's a Boltzmann machine. There is no restricted Boltzmann machine here. It's just, finding an interaction thing. So I'll talk next week about how this can be done for neuroscience, but let's forget about that. It's a non-trivial calculation, but there are some polynomial efficient approximations, so let's assume you can do that. So now you can redo exactly what was done in the case of correlation, but instead of defining the Frobenius norm of a correlation, you can compute the Frobenius norm of the couplings. And now it's a perfect match. It's a typical best case, right? I mean, it doesn't work so well for all proteins, but if a protein is not too large and the number of sequences is not too small, it works really well. And actually, this is essentially state-of-the-art approach for structural prediction from sequence data now. In fact, it was the winner of a CASP 11. So it's a contest where people try to predict structure. So when people resolve new structure of proteins, before they publish actually the data, there is a contest where people try to predict the structure, and then it's compared to the real structure which was found experimentally. And so if you are interested, I can give you some references where people really use this kind of approach for real data. In fact, not only structural prediction are interesting, but also let's say more, structural prediction is very nice, but it's very qualitative in a sense. Here we use this estimator of the existence of a contact, which is totally, out of the blue, saying that large couplings are contacts. It's not obvious why this should be true. There is some intuition behind that, but no big rationale. And it's not at all quantitative. But there are other experiments which are much more quantitative and sophisticated, So one of them is here. So there are different papers, but it's growing, where people can actually measure the fitness of a protein. So what is the fitness of a protein? So there are many ways of defining it. In the experiment I'm showing here, this is how a bacterium having the protein will grow. Okay, so you have some conditions, and you measure the growth rate of a bacterium, so at which time it will reproduce. The colony is growing exponentially, and that will depend on the proteins on the genome of a bacteria. So what you can do is make some mutation and measure the growth rate as a function of a mutation. So it depends on the protein you want to modify. So here the protein is actually a protein which is a nasty protein. That's called a beta-lactamase. It's a very important protein for antibiotic resistance. So this protein is actually conferring antibiotic resistance to bacteria, to some class of antibiotics, because it cleaves some parts of the antibiotics. And essentially what it, so if a bacterium has this protein functional, then it will be able to survive to large doses of antibiotics until the dose exceeds to some value, some kind of critical value that people call the minimum inhibitory concentration. And let's say for each sequence of a protein, you can measure the corresponding minimum inhibitory concentration where the growth stops. Okay? So it's a measure of the fitness of the protein. So that means that if the minimum inhibitory concentration is very high, that means that the protein is very functional because it confers a lot of resistance to the bacterium. If it's low, that means it's a non-functional protein. So this is how the fitness is measured. This is the minimum inhibitory concentration. And what you can do is see whether actually the model you have inferred here is actually predictive of its fitness. Because remember, this probability here is telling you how much or how well the particular sequence of protein is actually belonging to the class of proteins that are functional, that are found in the databases. So if P of A is large, that means this is a good protein. P of A is very low, that's a bad one. So if this is a very good protein, that means the fitness of this protein should be very large, so it should resist a lot to the antibiotic, right? Otherwise, it should be bad. So the idea is to compare this score, which is obtained by this model, this computational model, from sequence data, to what you get when you do mutations around the wild-type protein, the protein which is actually corresponding to this particular bacteria. Okay. So you see, it's a highly non-trivial thing, because if you think in terms of sequence space, I mean, there is a very interesting problem here. If you think in terms of sequence space, that's my sequence space. Okay. So L is the length of a protein, so we are on 20 to the L sequences. Okay. Then we have sequences coming from very different organisms. They are far away in sequence space. So maybe some lab is a very powerful lab and loves a lot of organisms and has published a lot of data. So this is totally non-uniform. And there are organisms nobody cares about, and they should be here, but nobody cares. They are just not liked at all by anybody. But anyway, that's the kind of thing you have. Now you take one organism, one specific one, and you ask, what is going to happen if I do mutations around it? So you have this long protein, and you make single mutations. So obviously, all the mutants will be very close to that, right? You create a lot of mutants here, and you ask how the fitness is changing, how the properties of these sequences are changing. And you want to predict that from a model which is fitted from the white dots, which is a totally global, large-scale model. It's not at all obvious that anything like that should work. Okay? And in fact, the only reason why these kind of things should work is that there is some kind of regularity or smoothness in this model. Otherwise, it cannot work. So what you see is that, in fact, there is some kind of correlation. It's very far from being perfect, right? So there are other, I mean, if you are interested, you can look at this paper where this was done for many different families of proteins. So there is some correlation. It's far from being perfect for different reasons. First of all, because the experiments are far from being perfect. There is a lot of noise. Secondly, because the model is far from being perfect. Third, because the connection between the what is measured and the model is very far from being obvious. So that's a lot of very far. In particular, for instance, people measure fitness by they measure the stability of a protein, which is only one ingredient of a fitness. It's only a part of it. So obviously, this P of A should contain many other terms which are not taken into account in the experiment. Anyway, so I wanted to mention that because I think it's a very interesting problem. Okay, so this approach has been very influential, trying to find effective interaction, but this is not the only approach that people use in order to understand the correlations between different amino acids in proteins. So another approach is essentially based on PCA, things we talked about in the previous weeks. And the idea is very simple, that, okay, you get a bunch of data, you can compute the covariance matrix and then do PCA and find specific directions which matter more than others and do dimensional reduction. And when you are in this low dimensional space, maybe you find clusters of sites which are very strongly co-evolving together. And this approach was pursued by many people, but especially by Rama Ranganathan and Stan Leiber and collaborators. And this is for one particular protein. So let's look at the WW domain, which is this small one here. If you do that, you can find clusters of sites which seem to be evolving very strongly together. That is, if you go from one sequence to another one, from one organism to another one, clearly this amino acid cannot evolve independently. And the idea is that these amino acids, for instance, are responsible for the binding and the specificity of the binding of the ligand. So they have to co-evolve in a concerted way in order to maintain the function. Okay, so there are different problems with all these approaches. So if we take the approach with the effective interaction, the pairwise interaction, I think obviously it's a very successful approach, but it has some conceptual problems. I mean, one of them is that mathematically, if you look at that, probabilistically, the model means that you would like to fit all the pairwise correlation and no higher order correlations. That is very hard to accept, right? Why should all pairwise correlation matter and no three-body correlation? It's very hard to accept that. So that's one thing which is very far. Of course, you can fit higher order correlation, but then you need a lot of parameters, and there are not enough data to infer all of them in a nice way. So this is a major limitation. The second thing is a more, let's say, conceptual limitation. I think we have also in physics. If you think about that, you have the data, and there is a huge effort which is done in order to find this Jij. But then once you have the Jij, we basically understand nothing, right? We can rank the big one, and that's fine, but we don't understand anything. If you think about spin glasses, you get the Jij for free, you are given them, and it's very hard to understand how the measure of the configuration space is done, right? It's a very tough problem. So having the Jij is not the final answer to the problem, it's just the beginning of the answer. So in particular, we do not understand what are the collective excitations. How do you get these modes, which are found by PCA, from the Jij? It's not easy at all. Another problem here is that, as I said, the functional protein is not a single thing. It depends on the stability, affinity, whatever, many different aspects. And the model gives you only the energy. You have a single number for sequence. You would like to be able to decompose the sequence in all these aspects. So this is clearly missing here. Yes?
Just a question. I was always wondering does it make sense to also try to fit other things than correlations, like some other properties that you can see from data? I don't know.
Well, I mean, other observables.
Right, because one always, like the story is always we have the single-sided pairwise correlations, there's the inverse model, if both sides that would be spin, but it would be too many. But I wonder if it would make sense to try to constrain some other observables than the correlations.
Yes, so the question is how do you know the observables? The problem is that people don't know the observables. They don't know what kind of combination of amino acids are important. Right. So the whole question is finding these observables. And in fact, fitting the pairwise thing is just a way to get around that, but without understanding anything, right? So maybe I'll talk about that again, about neural networks. So people have put other observables, like the mean activity or this kind of more global observables. That helps fitting the data. But in the case of proteins, we don't really know what's important. And I think the whole problem is to find that. Find these clusters. But what is the important information we should constrain on? Okay, so I would like to show you application of this RBM I mentioned before the break. So I'm not sure I will have enough time to do that, but maybe I can show you just some example. So this is again the same machine. Now the only difference with what I've shown before is that we don't have visible units which are 0, 1s, but they take 21 values. But it's a purely technical change, right? That means each visible unit can take 20 amino acid values of a gap symbol, but it doesn't change anything. And the log of a joint distribution of A and the H, the hidden layer representation, is given by this thing here. You recognize the effective potentials, the local fields, and the interaction term, which is, usually people consider only this thing here in the pairwise interaction term. So one important thing about this RBM here is that you can compute the marginal, and this is what we should do in order to train the model to find the couplings. But you can do much more than that. You can compute the conditional distribution of a representation given the sequence, and that's a way to extract the representation from the sequence. And you can also generate new sequences given a representation. That's the conditional distribution of A given H. So this is very important for design. How you design new sequences. If you understand what matters in your sequence from this step here, then maybe you can generate new sequences, completely different, but having the same features. So if I want to represent that, you have your sequence space. So you have different axes corresponding, this is AI, not VI, corresponding to the different amino acids. So you have 21 different values along each axis here. So it's the L-dimensional space, where L is the length of protein. You have different natural sequences, which are dots. They have different functional aspects, which correspond to the color of the dots. And you would like to go to a representation space where actually you could understand something about the biological properties. And maybe if your machine is good enough, and you are good enough to train it, then the axis here of the H's will actually mean something. Maybe this H here will control the specificity of a protein. This one will control the activity. Another one will be important for structure and so on. This is a dream, right? If we are able to do that, then we can go from this space to this one through this conditional probability and go back through this one. Okay? So I'm not saying that RBM are the final solution to this problem, but I mean they are a practical solution, even imperfect solution, to the genotype-phenotype mapping, because they do that. They tell you if the H's are aligned along the phenotypic direction, I mean the biological features, then they should tell you how you determine the phenotype from the genotype and back. So let me show you some results on 2 different families of proteins, and all these things were obtained by Jérôme Tubiana, who is doing his PhD at ENS. So there are the trypsin inhibitor and the WW domain I already talked about. They are short ones. So let me show you so you train these things here, and you get 100 hidden units. So you will see how the characteristic depends on this number here. And so we pick up some hidden units here, and I'm showing you the weights, how they are connected to the sequence. So this is for this is the trypsin inhibitor. So you see here the 3D structure. So you get 2 antiparallel beta strands and 1 alpha helix. Well, there are 2 alpha helices, one at the 2 extremities of the protein. So this is the first hidden unit. So the representation is the following. This is the index of a site. So it goes from 1 to 53. This is the weight. So the weight should be W. Here you have Wi mu of A. So mu is the index of the hidden unit, which is 1 here. So I goes from 1 to 53. And A is the amino acids. So you have 21 amino acids or symbols. That means we have to represent on each side 21 numbers. So we use what people call the local representation. So here you have negative values. Here you have positive values. And you get 21 different symbols. And the size, and so the Wi of K, so this is, or C, let's say the cysteine here, that corresponds to negative things. And the size of a coupling is proportional to the height of a letter. And we have different colors for the different amino acid characteristics. Is it clear? The representation, more or less? So it means here, for instance, on site 45, you know, for instance, for arginine, you have a very strong negative couplings, okay? And here you may have very strong positive couplings and so on, okay? So you see, this hidden unit is basically seeing nothing because all the couplings are very small, except on two sites, 49 and 45. And it basically, looking at two sites on the sequence, it turns out these two sites are in contact along the sequence. And the color of the amino acid here indicates the charge of the amino acids. Red, negative charge, blue, positive charge. So it makes sure that a strong activation, either strong positive or strong negative activation, which in both cases correspond to the important part in the potential, then correspond to amino acids of opposite charges next to each other. And that's a very good way to stabilize the alpha helix. In fact, if you look a little bit carefully here, then on site 53, you get exactly the same alternate pattern here, but much weaker because not all sequences in the database have the total length. But the signal is there. That would correspond to another amino acid here. And the helix turn is 3.6. This is very close to the 4 you can see here.
Sorry, here is for a given mu.
That's a given mu. So it's one mu we have picked. Again, I'm choosing some mu. We understand here carefully. I'm showing you. So this one, this hidden unit, is basically looking at these two sites and making sure that it contains two amino acids of opposite charges. That's another one. I will show you 5 of them. So I hope you won't get bored by the 6. That's the second one. So this one is also a structural mode. So it looks at 2 amino acids at the extremity of this beta strand and 3 amino acids next to each other on the other beta strands, which are next to each other. And you know, here the interactions are more complicated, but that's a collective structural mode, which makes sure that actually that these two things interact properly in order to have these contacts, which are realized at the end of the beta sheet. And on the other side, it's essentially 0. Whatever happens on the other side doesn't matter. More interesting ones. So here, well, I mean, again structure, but alternative structure. So it's a bit more subtle now. So if you look at this weight here, this hidden unit is doing exactly the same thing as before. So now on side 11 and 35, you can have a cysteine-cysteine bridge, which is very strong, almost covalent bond between 2 amino acids. So this is a very good way to maintain very strong contact. And now, if we do something that is similar to what people do in PCA, so we plot here along this axis the inputs to this particular hidden unit, and each dot corresponds to a natural sequence, you see essentially 2 blobs. I explained what is the axis here, but imagine it's just a histogram. You see 2 blobs. One corresponds, the major part of the sequences have very strong negative activation that correspond to the cysteine-cysteine. So most sequences here of the trypsin inhibitor have this cysteine contact, but some don't. And they all come, or essentially all come from nematodes, which is a small worm. Now, what is going on from these nematodes? They are doing something else. They have lost the cysteine-cysteine one. So what can they do? So a part of them, corresponding to this strong activation here along another hidden unit, that is here, they do something nice. So you see, you get 1 negatively charged amino acid here and 2 positively charged here. So instead of having cysteine-cysteine interacting together, they have built a mechanism where basically you have 2 positive charge here and 1 negative charge here, which are taking into sandwich this negative charge here. So it's another way to have a strong contact. So it's a way that nematodes have found here to stabilize the same structure. So you see completely different realization, even from a physical point of view, of the same structure with completely different sequences and types of interaction. Okay, so maybe this one is more complicated. So let me show also that how also the specificity and the functional specificity of sequences can be found. And I will maybe know that. So I don't know if I should. Should I stop at 12 precisely, or is it okay if I have 5 more minutes? Or yeah. Okay, so this is on WW. So WW is this short protein domain, which is made of 3 beta strands, anti-parallel, that you see here, the secondary structures, beta 1, beta 2, beta 3, which are linked together by loops. So let's say more floppy parts of a protein. And what you see here is the sequence label. This is just telling you the 1-point statistics in the sequence data. So there are two sites, 5 and 28, where W is very strong. That means the tryptophan has a very high probability. This is why this is called the WW domain, because W is the letter for tryptophan. So those that have a big meaning, that's the idea. So now it's known from biochemical studies, it was studied a lot because it's a short domain, that this WW domain can bind to different kind of peptide chains, which are all rich in proline, P, but the context is different. So classification right now is of 4 different types. And depending on, you see type 1, for instance, is that you have prolines which are followed by any residue antityrosine, which is an aromatic amino acid, and so on. This one is actually you have a bunch of proline and you have leucine in between, and so on. Okay, so, and people know that if you present any kind of peptide chain where you see these motifs, then a part of the WW domains will bind to that, another part will not, and all the WW domains which bind to them are called of type 1, and so on. This is the classification which is somewhat empirical. The question is, how do we see that? How do we understand which elements in the sequence are responsible for that? So you can isolate actually several hidden units which are responsible for that. So for instance, these hidden units here, that is interesting. So this is actually located, you see, on the first beta strand, and also essentially in the loop in between the two, and beta 2 and beta 3, which is very important for the flexibility of the structure. So the ligand is basically, when beta 2 and beta 3 come next to each other, like this, the ligand is binding on this beta 2, beta 3 pocket. So it's basically binding there, okay? But the specificity for a ligand can be controlled by what is going on over there. So it's not local, right? So the vision that actually everything which matters is exactly what the ligand binds is wrong, simply because you have to think that this thing is actually a very dynamical object. So the fluctuation of this thing actually matters a lot also for the binding specificity. So for instance here, and this is another hidden unit which is also very important, which is located also in the loop in between beta 1 and beta 2, mostly. So here in this two-dimensional plot, you see the dots which correspond to the hidden, so the activation, the inputs coming onto these two hidden units, and for all the natural sequences that correspond to the gray dots. So you see a clustering into some blobs here. And now for all the sequences where the type is known, which is a very small fraction, so all the sequences where the experiments were done, you see clearly the cyan one, they cluster here on this blob, that is negative inputs on this hidden unit, positive on this one, okay? And that correspond to all the type 1 proteins which are known. The type 4, there are not so many of them which are known, they are here, and type 2 and 3, they are here. Okay? So it seems that these hidden units are able to separate the different clusters of ligand specificity. You know, it would be very hard actually to find that without this kind of data analysis. So I will stop, but I want to mention another thing we can do with that. So we can do conditional design, and this is important for protein design. You know, the idea is this thing. Essentially, what we have done here is this arrow. You pick up the natural sequences, and you see what kind of representation you get. But now you can do the other way. So how can you do the other way? Well, what you can do is say, okay, so this is exactly the graph I mentioned to you before. Remember? This is the two-dimensional plot of activation of these two hidden units here. Now what we can do is actually take our machine, once it's learned, and we can tweak its activity in the representation layer. Let's say activate very strongly these hidden units, or this one, and generate a bunch of sequences here and see what they look like, how they will project. And you see, for instance, you can generate a lot of things here. So the gray one, again, are the natural one. But now all the other ones, the colored ones, are the ones which are artificial sequences. And you can see, in particular, we can find sequences which are putatively of type 1, of type 4, or type 2 or 3. And we can even populate this thing here, sequences which are never found in nature. Now the question is whether they are functional or not. So we need some people to do experiments. But they seem to be okay. you can compute, for instance, the probability of the scores of these sequences given by the machine, and they are actually pretty high. So two things, the scores are very high, comparable to the natural sequences, and they are not just minor variation of the natural sequences. If you look at the Hamming distance between these generated sequences and the natural one, they are far away. And I don't know if the RBM is actually doing something nice or not, but it has to be like that. I mean, intuitively, because maybe the RBM is not powerful enough, and what we are saying is wrong. But I mean, the important point is that there should be a huge entropy, a huge way, many different realizations of proteins with a given function. Otherwise, how could evolution find them, and so on? And how could that evolve? So it makes a lot of sense to have these kind of things. So maybe I would like to finish with a couple of slides on the compositional aspect, this third phase of the Hoffa model that we find before, and see what it means here for proteins. So again, we are in this problem here. We have a sequence space, we have a bunch of natural sequences we like to fit this probability distribution. Okay? So there are many different ways you could use in order to do that. One way, maybe the simplest one, is to have a mixture model. So if you use RBM to have a mixture model, this is exactly what you would do in the ferromagnetic phase of a Hoffa model. Because if you are somewhere here in this sequence space, there you are aligned maybe along the feature of the first hidden unit. It will be strongly activated and the other one will do nothing. So you have a prototype coding for this part of the sequence space. You have a prototype for another part and so on. And essentially you are activating all hidden units one at a time, and they're all prototypes for a part of the sequence space. It's a mixture model, essentially. That's one possibility in the ferromagnetic phase. You could have something much more complicated, which is the glassy phase. Actually, there is no reason why the glassy phase is bad. Maybe it's bad for us, but I mean, it might be actually good to represent the data. You can train the machine in the glassy phase or some kind of glassy phase, and that means that all hidden units are activated more or less in the same order of magnitude. You change from one sequence to another one, they change a little bit from each other, okay? And essentially, you may find a good score. Everything is nice, except that we don't understand anything, because all these hidden units, they are activated together, maybe a bit more, a bit less. How can we interpret anything about their meaning? So it's not that the glassy phase is intrinsically bad, it's just that we don't understand anything. Or you could have another representation where you have a bunch of features which can be recruited all over the place, but not in the same combinations. Okay, so for instance, this feature here will code, the orange one will code for the contact between site 11 and 35 being cysteine-cysteine. This can be true in mammals, and this can be true also in bacteria, but it's not true in nematodes. Okay, this one will code for the specificity to type 1 ligand, which is true here and here, but not in another region here. And now the combination of that, and there are many ways you can combine, will define the sequence. And this is much more similar to this third phase I was mentioning. And this is much better. So, and this will be my last slide in two parts. The issue of sparsity is very important, because otherwise you end up in some kind of representation like that where this is very bad. So we want to force this kind of representation. And as we saw from the phase diagram, the sparsity of the weights is absolutely crucial from that. So here, you can see the as a function of the sparsity, which is really forced by putting some prior. You can see the likelihood of the data on the training set and the test set. So maybe here, look at the test set for the rectified linear units, which is this one. I mean, double rectified linear unit. So the important thing is that when we don't impose any sparsity, the likelihood of the data is increasing because we are not putting any constraint. This is totally clear. In fact, this is why I'm saying these kind of things can fit the data really well. Now we impose sparsity, and the thing that has to be understood is the following. The likelihood decreases very mildly unless you go to too sparse models, and then it's a disaster. But if you stop here, then you get representation which we would like to think makes sense. So here, that's the kind of feature you get. Whatever you may understand from that, I don't know. But it's very hard to say anything. But here, this is what you get, which are much easier to understand from a structural point of view. Okay? Now the question is why we have this huge plateau here. So there is a huge diversity of solution. It's totally entropic. and we don't understand why this is like that, but it seems a very general feature. And among all these solutions, some can be interpretable, otherwise I think they are not. So I will stop here.
Are there questions?
Too late, too hungry.
Let's take the questions for the lunch with the speakers, so we'll leave in about 10 minutes.